And so what we will discuss today, I hope to cover 4 topics. Number 1 is I hope to introduce the high mountain Asia, and also broadly the context of climate change and the glacier degradation in the high mountain Asia, followed by the slope instability, outburst flux, erosion and sediment yield in response to the amplified climate change and the glacier degradation. And lastly, I hope to discuss how these changing mountain landscapes are affecting the mountain infrastructure. And this talk builds on these 2 papers, one published in this July in Nature Geoscience, and another one published in Science in 2021. And so the first question, where is high mountain Asia? I think this is really a nice illustration to show the where is high mountain Asia, that you can see the area above for the area above the 2,000 meter above sea level. You can clearly see the boundary. Basically, it means it includes the Tibetan Plateau and also the surrounding high Asian mountains, including the Himalaya here, the Karakoram, the Tian Shan in the north, the Kunlun here, and also the eastern Tibetan Plateau mountains, including the Hongduan mountain here. So for the high mountain Asia, it is really a fascinating place for our Earth scientists. I think many researchers from different parts of the world, they came here to study the climate, the glaciers, permafrost, river systems, water resources, and of course tectonics, earthquakes. And for us, we study the river sediment in the region. And the high mountain Asia has many names, right? It is the roof world, and also the third pole. For example, it's called the third pole because it has the world's third largest glacier and the permafrost systems, just following the 2 polar region. So it is called the third pole. It is also the Asian water tower. So from this figure, we can see all these large Asian rivers, including the Yellow River, the Yangtze, Mekong, Salween, Ganges, Brahmaputra, and Indus River. They all originate from the high mountain Asia, which means these large Asian rivers, they provide water resources for roughly 2 billion people, which is 1/3 of the global population. So they are super important large river systems. And for our geomorphologists, we also study this river because these large Asian rivers, they contribute huge amounts of sediment to the ocean. And from this classical map by John Milliman, we can see that these large Asian rivers, they contribute roughly 25 to 30% of the global land-ocean sediment transfer. And in response to the global warming and the climate change here in the high mountain Asia is very fast. And from this left figure, some of you may have heard the term called the amplified Arctic warming. Amplified Arctic warming basically means that the Arctic is warming much faster than the global average. And this is very similar in the high mountain Asia or in the third pole. So from this figure, we can see the red line here is the Arctic, and the blue line is the third pole, right? So we can see the temperature increase rate in the third pole is very similar to that in the Arctic. And from the red figure, so we collect data, climate data, including temperature and precipitation from over 100 climate stations in the entire third pole region. And we found that the temperature increased steadily, and after the middle 1990s, the increase accelerated, and on average over the past 6 decades, that the temperature increase rate is 0.32 degrees Celsius per decade. This is the doubling the global average. And precipitation here in the region also overall increased in the past few decades, especially after the middle 1990s. So we can call that the high mountain Asia is becoming warmer and wetter. So what will the consequences of the amplified climate change? As I mentioned before, there are many huge amounts of glaciers and also permafrost here. And in response to the temperature increase, that from this map, we can see this is the elevation change rate of the glacier. So you can see all the red dots here. It means that the negative glacier mass balance basically means the glacier is thinning and also retreating. And especially in the Himalaya part and also in the southeastern part of the high mountain Asia, we can see the very red dots. And it means that in the in the Sample Gorge area, nearby the gorge area, that the glacial mass balance is close to -1 meter per year. Basically, it means that if the glacier is 10 meters thick, that after 10 years, the glacier will be gone. So you can see very fast climate change signal. And also here, this two photos very clearly show that the glacier, how fast that the glacier have been thinning and retreating over the past decades in response to global warming. And also modeling studies suggest predict that even under the conservative climate change scenario in the future, by the end of the 21st century, 40% under the conservative climate change scenario RCP 2.6, that 40% of the glaciers in the region will be lost. And if it is under our business as usual climate change scenario RCP 8.5, that 70% of the glaciers in the region will be lost by the end of this century. And in addition to glaciers, permafrost is also important, right? So what is permafrost? Permafrost is the frozen ground beneath our feet. So you can see from the left map, you can see this is a global scale study that report that the increasing permafrost temperature since the 1980s. Of course, including the high mountain Asia, the permafrost temperature is increasing. So with the increase of the permafrost temperature, the top layer of the permafrost that is called active layer, the thickness of the active layer will increase, which means that the ground ice could be melted. When the ground ice is melted, that it can destabilize the landscapes and cause subsidence and also source lumps and many slope failures. So in addition to glacier, the rapid change of the glacier and permafrost, the mountain erodible landscapes are also expanding. What is the mountain erodible landscape? Here we introduce this concept. We define this concept as the most relevant landscapes, including the active glaciers, active permafrost, active fluvial channels that can contribute water and sediment fluxes in the cold mountainous environment. Basically, in this diagram, you can see the red shaded area. It's called the active mountain erodible landscape because they are contributing water and sediment to this catchment. And the area, the gray shaded area and the light blue shaded area, they are still frozen in a given day of a year. So they are not contributing water and sediment. And over the past decades, we can see in response to temperature increase that the erodible landscape in the mountainous areas are also expanding. So the cryosphere, including glaciers, permafrost, and erodible landscapes are changing. It will has huge implications for the slope failures and also extreme hazards. For example, here I will show an example of this is a ice avalanche event, and so basically it occurred I think a few months ago in Tian Shan, that a huge chunk of ice just collapsed from this mountain peak. And here is another example. Many of you may have heard this one, the Chamoli in the February of 2021, the Chamoli rock ice avalanche event that has this one a huge chunk of rock and ice, basically roughly 27 million cubic meters of materials. They falls down and over 2,000 meters, and falls into this glacial valley. There are a lot of unconsolidated material in this glacial valley, and the melt of the ice has triggered the debris flow and swept away these two hydropower projects. And this one has caused the deaths of over 200 people, including most of them are the workers in this hydropower project. So it was really a huge disaster, not too far away from us. And in addition to the slope failures, there are also extreme floods. Here, the flood is kind of different from the monsoon flood. It is called the outburst flood. For example, here all these red diamonds here in this map, they are the historically reported glacier lake outburst floods. And now I will show a example of the glacial lake outburst flood. It is a transboundary event. So basically here it is the Tibet of China, and there is a small glacial lake here. You can see more clearly from this image. And here is the boundary between China and Nepal. And here is the destroyed hydropower project. So you can see that during a heavy rainfall event, there's a debris flow from the upstream of the glacial lake. They flows into the glacial lake and caused the failure of this marine dam and triggered the downstream flooding. And you can see the magnitude of the outburst flood is 5 to 10 times higher than the typical monsoon flood. So they are very destructive to the downstream infrastructure, including the hydropower project and also the roads and the houses. So the question is, are these slope failures and extreme outburst floods what is the causes of these unstable landscapes, and are climate change responsible for this extreme hazards? Now I will explain these processes from using the theory of paraglacial theory. So what is paraglacial theory or paraglacial geomorphology? So this theory proposed by Professor McButcher from UBC Geography. And so basically it means that when the glacier retreat, and for example, this is the blue dotted line here is the glacier elevation in 1950, and in 2100 we can imagine this with glacier retreat, this glacier terminus line shifted upstream, right, to here. And this newly exposed landscape, they are called the paraglacial landscape. They are very unstable due to the debus tracing effect, and they are prone to the mass wasting processes, including the landslides, debris flows. And for example, here is an example in June of 2020, also in Tibet of China, and it's a landslide from this newly exposed paraglacial zone forced into the proglacial lake, and triggered the displacement wave, and also overtopped the marine dam and caused the failure of the dam and the downstream flooding. And another example is the Yigong landslide lake outburst flood. And in this case, it occurred in 2000, and a landslide from the proglacial area dammed the Yigong River and formed this landslide-dammed lake. And the landslide dammed the river for over 2 months before the breaching. And when the lake was breached, it caused a super high magnitude flood, and the peak discharge of this flood was estimated to be 120,000 cubic meters per second. This is so-called the largest or the highest magnitude flood event in the region over the past 100 years. And if we summarize such processes, we can see climate change has caused the deglaciation, and the newly exposed paraglacial landscapes, they are unstable. They are prone to landslides, debris flows, and rockfalls, and they can further trigger the lake outburst flood. Of course, climate change can also expand the glacial lakes. For example, here, if we look at this, this is a proglacial lake with climate change that the increasing glacier melt. This lake will expand due to more meltwater into the lake. So when the volume of the glacier lake they increase, they can sometimes also overtop the marine dam and cause the lake outburst flood. Of course, climate change can also increase the precipitation extremes. They can also exacerbate such hazards. So far we know that the temperature in the region is increasing, precipitation is also increasing, glacier is retreating, and permafrost is thawing, and the erodible landscape is expanding. And our next question we hope to address is, can we see the climate change impacts on the river sediment in the region? This is the question that we hope to address. And now I will show the results first. So to answer this question, we first collect data from 28 high water basins in the entire high mountain Asia. And our including the river runoff data and also river sediment flux data from the 1950s to 2010. And the results show that both annual runoff and also sediment flux, they have been increasing over the past decades. And for the river runoff, the increase rate is roughly 5% per decade. And for the river sediment, it is 13% per decade. And if we divide the high mountain Asia into two parts, the HMA eastern part, the HMA west part, that is mainly affected by the westerly controlled climate zone, including the upper Indus River Basin and also the upper Tarim Basin. So we can see, as compared to the monsoon affected region, in the westerly controlled river basins, both the runoff and also the river sediment increased much more drastic as compared to the monsoon controlled region. And here, this figure shows the time series of the data, including we can see the river runoff here increased steadily, and after the mid 1990s, that the increase accelerated. Similarly for the river sediment flux, and it increases since the 1960s, and gradually, and after the mid 1990s, the increase accelerated. This is in response to the warmer and wetter climate. Here, the temperature data, this blue line, and the precipitation data, this green line. After the mid 1990s, the region has become warmer and wetter, and the glacial retreat also accelerated. With increasing glacial retreat, that the glacial erosion could be enhanced due to the more meltwater below the glacier, and because the glacial meltwater is also temporarily increasing due to the temperature increase, and the increased meltwater, they can transport the materials to the downstream. And in addition to the glacier's permafrost is also important because roughly 50% of the landscapes, they are underlain by continuous permafrost. So with climate warming, that the melt of the ground ice, they can cause destabilize the landscapes. For example, here it is an example of the permafrost source lumps, which means that a huge amount of sediment from the permafrost slopes, they can be transported to the river systems when they are connected with the river. And remote sensing data also suggests that over the past decades, the permafrost source lumps in the region have increased over the past decades. And here in this diagram, I want to show that how the temperature and the precipitation, they can control the discharge and also the suspended sediment in the region. And here is a very nice daily data to show the process. For example, here I identified 5 sediment pulses. Basically means when the sediment concentration is over 2 kilograms per cubic meter. And the number 1 event, it is called it is response to temperature increase driven snow melt processes. And the number 2 and number 5 event, it is a very typical rainstorm driven sediment events. And here the number 3 and number 4 events are something interesting because in cold mountainous environment, the temperature, we show that the temperature is also very important because during these 2 events, we can see the precipitation is very low, basically close to 0. But there are 2 temperature peaks. Yeah, there's a gray line here, which means that the temperature increase can result in the glacier melt and also the permafrost ground ice melt. They can contribute water and sediment. So here I want to say that in the cold mountainous environment, in addition to precipitation, temperature is also a very important control of the hydrological and geomorphic processes. And so we know that temperature and precipitation is important. So we, based on the data we have, based on the river sediment, and also the climate data we have, we estimate the sensitivity of the river sediment flux to climate change. Here the results show that for every 10% increase in precipitation, it can result in a 24% increase in the river sediment. And for every 1 degree increase in air temperature, it can result in a 32% increase of river sediment. And interestingly, we found that for for a river basin where there are more glaciers, which means the glacier coverage is larger. Their sediment flux is more sensitive to temperature warming. Yeah. So with such a sensitivity result, and also with the future climate change scenario that we predict that by the middle of the 21st century, by 2050, roughly, in the region, because the climate model, they predict that in the next few decades, the climate here will continue to become warmer and wetter. So under the extreme climate change scenario, which means that the temperature increased 3 degrees and the precipitation increased 30%, that the current fluvial sediment in the region will increase from the current 1.9 gigaton per year to over 5 gigaton per year by the middle of this century. And we also compare our results with the Arctic. For example, there are two findings. The number one is that currently the mean annual river sediment flux in the high mountain Asia is larger than that in the pan-Arctic rivers, and also bigger than that in the Greenland. And secondly, we found that the river sediment in the high mountain Asia, they are more sensitive to climate change than that in the Arctic. Okay, now I will discuss the impacts of the changing river sediment on many other factors. For example, why do we study the river sediment? It is very relevant to the hydropower, agriculture, water quality, carbon, and flooding. And for example, the water quality. So we know that the river sediment in the Himalaya rivers, they are increasing, which means that the stability of the Himalaya rivers can also increase, right? And in the glacier and permafrost systems, a lot of they contain a lot of mercury, heavy metals from other sources, and in response to the temperature increase, such heavy metals could be transported together associated with meltwater, and the fine particle of the sediment, they really the heavy metals, they can affiliate to the fine particles of the sediment and cause the potential degradation of the water quality in the Himalaya river. So you can see this image here. And also importantly, sediment is also relevant to the river particle carbon, and especially for the high mountain Asia, that as I mentioned before, 50% of the landscapes is underlain by continuous permafrost. And the permafrost, we know that the permafrost, it is the Earth's largest terrestrial carbon sink, and much of the carbon, they have been stored in the permafrost, frozen permafrost landscapes for thousands of years, and due to the rapid and amplified climate change, that they can be released into the river systems together with the sediment in just a few decades. And our study, we estimate that under the extreme climate change scenario, by the middle of this century, the fluvial particle carbon in the region can be 50 to 150 million tons per year. And the flux. So river sediment is very relevant to flux. Here is a very nice common paper by Jim Best, Peter Ashmore, and Stephen Darby. They basically published in Nature Sustainability. So basically, they argue that when we are looking at the flux, we should not only focus on the water, how many water, or what should not only focus on the peak discharge or the hydrological perspective. We also need to look at the sediment, because sediment is really plays an important role in the flux. For example, when there are too much sediment in the river systems, for example, here is the example of the Kosi River. It is a transboundary river from the Tibet and then to Nepal and then to the India, downstream India. So roughly at the boundary between Nepal and India, that is the mountain exit. So the river sediment from the mountain systems, when they exit when they arrive the mountain outlets, the river began to expand. I mean, the river width increase and the flow decreases, river flow decreases, and a lot of sediment, they can be deposited in this alluvial fan. And with time increasing, that the riverbed of this here in this mountain outlet river, they can very high. And when the riverbed is as high as the floodplain, and during the flood event, they can easily trigger the river avulsion. For example, in this 2008 Kosi River avulsion, it has it caused very severe impacts to the local communities. And also importantly for the hydropower, I hope to have a few slides for this hydropower systems in the context of climate change. So hydropower is very important, right, for this high mountain Asia countries, Nepal and for the Nepal and Bhutan, almost all of their energy sources rely on the hydropower. But the question is, are the hydropower sustainable in the context of the climate change? And for example, we can see from this map that they are continuing to plan more dams in the region. For example, all these blue dots here, they are the planned hydropower projects, or some of them are under construction. And if we look at these blue dots, they are very close to the glaciers and also very close to this historically occurred gulf locations. So they are likely to face more higher risks in the context of climate change. And now I will show some examples. So we summarize these processes and have a perspective paper in Nature Geoscience to show that the climate-driven landscape instability, including the slope instability, including the extreme frost, and also the increasing river sediment, they can have very negative impacts on the Himalaya hydropower systems. They can not only cause the dam failure, for example, in this Chamoli event in India Himalaya, it has the debris flow directly destroyed this hydropower project, and also this glacier lake outburst flood, it destroyed this upper Koshi hydropower project in the Nepal, and also the increasing river sediment can cause the turbine aberration of the hydropower systems. The increasing river sediment also have implications for the hydropower systems. For example, when there are more river sediment from the upstream mountains, it can be when there's a dam, the river is dammed, most of the sediment will be trapped behind the dam. And using the example of the Upper Yangtze River, we estimate that over the next 3 decades, there will be roughly under the extreme climate change scenario, there will be roughly 2 gigaton reservoir sedimentation. It is a large number if we compare the volume of the deposited sediment with designed storage capacity of the reservoir. We can see it is roughly 2 times the designed storage capacity of this downstream Liyuan reservoir. So far, it is the first most upstream reservoir in the Upper Yangtze River. So other solutions, I mean, climate change are affecting the hydropower systems in the high mountain Asia. So the Straits Times, they report our study, and I think they very nicely summarized the threats of the climate change relevant threats to the hydropower systems in the Himalaya, and also give the solutions. So of course, we need to better understand the high risk areas where the locations they are more classified as high risk areas. And of course, in addition to climate related high risk areas, there are also earthquake related high risk areas. And also we need to consider the sediment issue in future hydropower design. If we look at the IPCC report, when we search hydropower, mostly they only consider the impacts of the climate change on the changing river runoff, and then affects the hydropower generation. But you can almost never see that they consider the impacts of the climate change on the potentially increasing river sediment, and then affect the storage of the reservoir and affect their lifespan. And I think this is really something we need to consider, especially for these high mountain river systems. And so the hydropower in the Himalaya countries may not be very reliable renewable energy source. So we also need to diversify the renewable sources, including the wind and solar panel potentially. Okay, now I will summarize my talk. So climate change and cryosphere degradation are destabilizing the mountain landscapes and increasing cascading hazards, including avalanches, landslides, debris flows, and outburst floods. And the erosion and the river sediment have increased substantially over the past decades with accelerations after the middle 1990s. And in a warmer and wet future, we predict that the river sediment in the region will continue to increase and very likely to double by the middle of this century. And the changing landscapes and rising river sediment have important implications for the region's infrastructure, energy, environment securities. And they can directly or indirectly affect on 2 billion people's lives. And forward-looking design and maintenance measures and sustainable sediment management solutions that could help the transition towards climate change resilient hydropower systems. And here are the publications that I mentioned in this talk. Okay, thank you. Yeah, thank you again.